In this video, I'm going to talk about a little bit more on the electronic voting protocol. I think the electronic voting protocol is probably the most difficult protocol in network security. It is there is no perfect protocol yet, but there are some protocols that we have used. For instance, we mentioned the Helios voting protocol. So I am going to talk about Helios in connection to the three cryptographic primitives that we mentioned in the last video. However, the actual Helios voting protocol used today is a lot simpler. Okay, so I just use its name, Helios, to talk about this voting protocol. So first, let's review the three cryptographic primitives that we will use. So this is three cryptographic primitive. So these primitives are actually not straightforward. So they are not. They are kind of difficult to understand, but we just want to lay down what they are for. So the first one is interactive. Proof systems. So in this particular system, so what it says here is that if you have two parties, Alice and Bob, I think I use a different name. We use Peggy and Victor. So Peggy has a secret S, and Peggy wants to convince Victor that she has this secret S, but she doesn't want to reveal S to Victor. Yet Victor will still be convinced that Peggy possesses this secret S. So that's interactive proof system is about. And we look at how it may be implemented in the previous video. So I'm not gonna go through that implementation. So the second cryptographic primitive is, let's say, re-encryption. Re-encryption algorithm or scheme. Okay, what it really says here is that you have a message M, plain text message M, and then someone encrypts it, let's say using a key, encrypts it. It has a C, so you got a ciphertext. So now we can re-encrypt ciphertext, get another ciphertext C prime, and of course this can be done pretty easily. However, the trick here, well, the most important part here is I can decrypt. So I can decrypt C prime without knowing, in particular, what is K1, without decrypting this C using K1. So this will be some other key, let's say K prime, and then this will return M. So so this is important, and this can also be done using algorithm like encryption. So this is not data encryption, it's a public key, okay? So it's related to Diffie-Hellman, and then we have algorithm encryption, so this can be done. So we are not going to talk about the details also. So the next primitive is called, okay, it's called threshold PKC. So this is also related to public key cryptography. So what this means here is that encryption and decryption are done by a number or multiple let's say parties. Okay, and of course there is a requirement. There is a requirement of a minimum number of honest parties to carry this out. Okay, so this can also be done. Okay, so basically, so these M players, we can think of them as players. So this, let's say there's a minimum number, let's call it M. So there's M players, each, just like Diffie-Hellman, they each generate a random number, and then they compute either the xi, let's say xi is the random number they generated. Of course, it has a parameter p, which is a prime number, and then you have a primitive root, which is now let's call it g. So g is a primitive root modulo p. So each of them pick a random number less than p. Let's call them xi. call each of them xi respectively. And then they compute g to the xi modular p, and then this becomes a public key. So they put all of these public keys together. There's m of them. Basically, there's a product of these public keys, and then we can compute a private key, R. So this R is contributed by each of these members, right? So each of these separate secret. Okay, so then this R can also be so then this R can be recomputed by a minimum of n parties, reconstructed. So then you can think of this R is a encryption key and decryption key. Okay, so just think of these things in this way. Actually, in reality, of course, the construction is a little bit more involved, but let's say that we have a way to do threshold PKC. So now in the Helios voting protocol, and so as I said earlier, so the Helios voting protocol I'm going to talk about is actually more involved than the one that has been actually in use. Okay, so this is a web application. So here we are going to use all these three primitives, and in the implement the Helios, the one that's available for people to use is a lot simpler. Okay, it's much simpler. So I'm just simply using this name. Okay, Helios. Okay, so then we can, so this Helios is a trustee. Okay, so we have to put our trust to this system. So let's say Helios involves several independent trustees, right? So you say we have trustee 1, 2, and 3. Let's say this 3, or let's say we have m of them, right? So maybe you can say we have n of them, and in reality you may have more, but at least as long as there are m of them that will be honest, then we can carry out this voting. So then they collaborate. Okay, they collaborate to come up with. They collaborate. So they work together to come up with a threshold PKCs. So that means that they can that means to encrypt a message, they have to work together, and to decrypt a message, they also have to work together. And also, if some of them, as long as they are honest, and this can be done. And if you can guarantee at least M trustees, they are not corrupted, then this can be done. So in reality, you may have a little bit more, right? So you may add a little bit more, but as long as you make sure that there's a minimum number of M trustees or independent parts, okay, they are honest. Then they can carry this out. Okay. So then so now let's say we have a voter, Alice. Okay, so in this system, of course, for a particular election, and there's a ballot, right? So there's a ballot has this candidates or write-in or write-ins. So Alice maybe pick this, pick that, and then maybe write a few names. Okay, and then Alice will ask Helios to encrypt it. Okay, so I have it. So Alice has it encrypted. So then it has a, let's say, Alice ballot. Let's just call it A. And this is ballots. So she prepared this ballot. And then this is encrypted. It gets C. Okay, then Helios also returns a hash code of C to Alice. Okay, so Alice can actually seize H of C. Okay, so that's returned by the system. So by this threshold, C is obtained by the threshold encryption on the ballot. So maybe I put an A here, so this indicate that's A. So in this case, okay, so let me say a few words about election. So election, the most important part is one is to protect the voter. So we need anonymity, anonymity of voters. That means that a ballot cannot be traced to the person, to the voter who casts it, right? So that's the first thing. The second thing, it needs accuracy. So or ballots are tallied correctly tallied. 3, they should have strongly auditable. So maybe this is a auditable by anyone who wish to check the integrity. So this is to guarantee integrity. So integrity, okay. So now we're going back, we go back here. So, so Alice in the voting phase prepares a ballot, okay, picks what candidates on the ballot, maybe write in some of her choices, and then ask the system to use the threshold PKC to encrypt that ballot. Now remember, to do the encryption, these more than one independent parties needs to do it. So that means that none of the single party can do it. Okay, they need to cooperate. And so it gets a CA, and then the Helios returns a hash code of CA to Alice. So at this time, Alice can choose number one, to audit the ballot, to make sure, to see if it has been encrypted correctly. Okay, so the second is to cast the ballot. So Alice can do this step one many times, right? So Alice prepares a ballot, asks Helios to encrypt it. So the system does the encryption, and then gives Alice a choice whether Alice wants to audit it or cast it. So Alice could, in order to make sure its encryption is correctly done, so Alice can choose to audit it. And then after this auditing, Alice would need to prepare a new ballot, even though the choice would be the same, and ask Helios to redo the encryption, and ask Alice again, okay, whether Alice wants to audit the encrypted ballot or cast the ballot. So Alice can do this for a number of times until she is satisfied that her ballot was correctly encrypted. Then she can decide to cast the ballot. Okay, so that's this phase. And then Helios will post or published, let's say posts, I need to learn how to write this on the screens nicely. So Helios posts the encrypted ballot of Alice together with Alice's name on a bulletin board. Okay, so as you can see, the bulletin board has a lot of this, a encrypted ballot, the name, the voter's name, right? Lots of them. So that is a bulletin board. Okay, then of course, so the hope here is that some of the voters will check, okay, would like to check the bulletin board to see whether their encrypted ballot was posted, okay, and all right, so the next would be to ensure, now before we do the encryption, I'm sorry, decryption, before these Helios, before the system decrypt this ballot, so they need or before these ballots are decrypted and tallied, so they need to be de-associated with their voters. Okay, so that these ballots won't be traced back to the voters who cast the ballots. Okay, so this is done by something like a mixed net. Okay, so so this mixed net is to de-associate, or basically just mix the ballots, right? So mix the ballots, shuffles the ballots. Okay, I put a quote here. So so using two things. One is a re-encryption. And also use interactive proof. So this is for correctness. Actually to show, for showing, right? So this is to show that the shuffle, the ballots are correctly shuffled. To show that the ballots are correctly mixed. Okay, so just in case some server that does the shuffling wants to cheat by dropping some ballots or adding some new ballots, that kind of things. So what this is done here is, so let's say after all ballots are collected, for election. So let's say this set B, all sets are collected into a set B. So let's do a curly B. So this is a set of all ballots, and we're gonna mix them up, because in the bulletin board it has, so each decrypted ballot with its name. So we wanna mix them up so that there's no longer associated in any clear way with their voters' name, with their voters. Okay, so then the first thing it does is to re-encrypt each ballot, I'm sorry, each ballot B sub I. So re-encrypt. So now this ballot is equal, let's call it, this is encryption of, so this is encrypted ballot. So maybe I should use a different, this is encrypted ballot. So this is equal to the I. So I is a voter's ID. And we know this is a threshold PKC that encrypts BI, so we get CI. So this is encrypt each encrypted ballot. So this is, so after all encrypted ballots are collected, so we call it beta. I'm sorry, curly B. So we re-encrypt it and then shuffle or shuffle. So that means permute. Permute this, okay, the set of all encrypted ballots to get a so when we re-encrypt this, we get, let's get it, CI prime. So CI prime is equal to, put it here, re-encrypt CI. So this re-encrypt, okay. So then we shuffle these ballots CI prime to get, so let me, so shuffle these CI prime to get a new set. Let's call it B prime. Okay, so this is a curly B prime. So basically in here, we do re-encryption. All right. And then let's see. So this is 2, let's say 3. And then we will repeat the same steps to produce M random ballot sets. M random ballot sets, which means we do re-encryption on beta sorry. So we just do it 3 times. I'm sorry, m times. So we start from A, re-encrypt it, and do another one, do another one, do one. Each time I shuffle them. Okay, so let's say we get B1, B2, BM. So we want to make sure during this process, these shuffling are done correctly. Okay, each of these shuffles are done by these AM servers. Okay, so by the AM entities. Okay, so we need to know that this has been done, has been shuffling correctly. So then to do so, we use interactive proof system. Use interactive proof to ensure the shuffling is done, is correct. So what it does here is that, so somebody wants to ensure this, okay? So that means there's some auditors. By an auditor. By an auditor. Okay, so, and so what it does is the auditor, so the auditor will send in, will issue a random random string of M challenge bits. Okay, so let's call it C1, C2 up to CM. So each of these is either 0 or 1. So if CI is equal to 0, then this Helios need to show BI okay, BI is equivalent to what's corrected if CI is equal to 1, need to show BI is equivalent to BI pi. Oops, pi, sorry. Okay, so this is interactive proof system. If all the trustee parties are honest, of course, this will not be hard. to do it, they just need to remove the re-encryption by providing the random or the whatever used in the re-encryption to the auditor, so the auditor can make that verification. Okay, so that is shuffling. And then after shuffling, it will be the decryption. So then it will be decryption. Well, it's just tally. Okay, so each ballot will be decrypted. Well, is decrypted. Again, by the M entities in the system, they have to work correctly, assuming these systems are independently, right? So you have M independent system all run the same system, all run independent entities, all run Helios. So they will then work together to decrypt all these ballots and then tallied. Okay. And then, of course, the results will be posted. So we have a very important step is auditing. So anybody, if they choose to, anybody, of course, it could also be organization, right? Some kind of watchdog organization can download the entire election data. Okay, and repeat and verifies all steps are carried out correctly and all the ballots are counted correctly, are tallied correctly, and all the ballots are counted and tallied correctly. So what they need is to get the decryption key, okay, to what they need to do is to get what's needed to carry out the threshold PKC, then to verify these tallies, to decrypt the ballots and verify this ballots are correctly counted and tallied, okay, correctly tallied. So this is the voting scheme. Okay, so as I said, electronic voting is hard, okay, because it involves many things. For instance, in this particular system, we didn't mention coercion at all, but that should be a very important thing too. So nobody should be coerced to cast, should be influenced how, sorry, nobody should be coerced to cast their ballots, okay, to choose, okay, to vote against their bills, right? So to pick candidates against their bill, okay. So nobody should be coerced to do that for any democratic system. But in this voting scheme, in this voting protocol, we cannot guarantee that. Okay, so that is the end.